Hey everybody, we've already seen that ionic compounds can be reduced in terms of their formula because of the arrangement of the ions in a crystal lattice. So for instance, if you found an ionic compound to have a formula of Ca2O2, that would automatically reduce to the simplest ratio of CaO. But for a covalent compound, it doesn't really work that way. So for instance, you'll notice that C4H8O4 and C6H12O6, those are both real molecules, and those molecules have, in this case, glucose, it has 6 carbon atoms, and it has 12 hydrogen atoms, and it says 6 oxygen atoms, and that compound, that molecule, kind of sticks together in space. It's not in one of these crystal lattices. But both of these two formulas, you'll notice, both have a different formula that they could simplify to, CH2O. And so that might bring to light the 1 to 2 to 1 ratio that you learned about for all carbohydrates in biology. And so our job today is to identify this simplest ratio, also known as the empirical formula. This is not going to happen for ionic compounds, but it is going to happen for covalent compounds or molecules. And there's a little rhyme that we can follow to do this, and it's over here on the left-hand side. It goes percent to grams, grams to moles, divide by smallest, multiply till whole. It's pretty fantastic writing, I know. But we're going to step our way through that rhyme, and we're also going to talk about why it's doing what we want it to do on our way. So we're actually going to jump down to number 2 to begin today, because number 2 is a little bit more straightforward than number 1. So we're going to just save number 1 for last. Now, the first line of our rhyme is to take percent to grams. And we have a little trick up our sleeves. If we assume that we have 100 grams of any substance, then if we have 100 grams, if 12% of our substance is, carbon, for instance, then we have 12 grams of carbon, right? So we can turn percents into grams by simply assuming we have a 100-gram sample, and that just makes our math much easier. You could pick any size sample, but 100 happens to be the easiest. So we are going to take our compound that happens to be made up of 36.5% sodium in number 2, and we are going to say simply that 36.5% sodium, because we're assuming a 100-gram sample, will really become 36.5 grams of sodium. And I'll tell you why that was really helpful in a second. Now, you're going to notice that I'm going to skip some space here. I'm going to leave a little bit of space to jump down to oxygen. We're going to do the same thing. 38.1% oxygen becomes 38.1 grams of oxygen. And similarly, let's leave a little bit of space and let's jump down to sulfur. So 25.4% sulfur becomes 25.4 grams of sulfur. And so why was that useful? Why is percent of grams useful? Well, if we have grams, grams are a unit that is on the periodic table that allows us to convert to moles. So let's do that first, then we'll talk about why it's important. So if I have 36.5 grams of sodium, I know that I can convert from grams of sodium to moles of sodium because 1 mole of sodium from the periodic table has a mass of 22.99 grams. Simply, it's molar mass. So if you do that math, you will get 1.588. And I'm going to have all of these numbers that we're solving for here. I'm going to keep 4 sig figs for all of them, just because that helps with our next step. So 4 sig figs for these answers here. We can do the same thing for oxygen. 38.1 grams of oxygen. We know that there are 16.00 grams of oxygen in every 1 mole of oxygen. When we do that math, we will get 2.381. And then finally, for sulfur, we have 25.4 grams, but we know that in 1 mole of sulfur, it has a mass of 32.07 grams, and that is straight off of the periodic table. So if you do that math, you will get 0.7920. So this number that we've just calculated, that is the ratio of the number of sodium, oxygen, and sulfur atoms that we have, right? So said another way, I could write out a formula as sodium 1.588, oxygen 2.381, sulfur 0.7920, right? That's the ratio of the elements in my compound. And that's all well and good, except you're probably thinking, and you're right, that we have never seen a formula that looks like that, right? We don't deal with decimal points like that. What we want is whole numbers. And so how do you turn this number into whole numbers? And by the way, remember, this is a number of moles. So it's a ratio of 1.588 moles of sodium to 2.381 moles of oxygen to 0.7920 moles of sulfur. Well, here's our next little trick. So our next trick on our rhyme says divide by smallest. So we're going to find the smallest of these three numbers. And you'll notice it's the green one, right? That's by far the smallest. And we're going to divide all of these numbers by that smallest because that is going to set this bottom one equal to 1. And it's basically going to tell me how many of that smallest number fit into these other larger numbers. So for the blue one, it turns out that that division equals 3, aka oxygen is 3 times as prevalent as sulfur. And up here, if we divide by 0.7920, we will get the number 2. So really, this ratio, when we simplify it, turns out to Na2O3S. Right, and that looks a lot cleaner than what we see up here. And actually, we can make this one step cleaner because we know that typically polyatomic ions end with oxygen. They're not in the middle. So really, let's write this as Na2SO3, which we should recognize as sodium sulfite. Bingo. Now, there's another question here. We happen to get a really nice, clean set of whole numbers here. What if these weren't nice whole numbers? That's a great question, and that's a question that we're going to save until we jump back to number 1. Before we do, let's try number 3, and let's do a similar job, except this time, instead of being given percents like we were in number 2, we're just given masses. And so that makes our life a little bit easier. We don't have to do this percent to mass step. We simply start with the mass, and we're going to turn all of these into moles. So for nickel, we have 0.0015 grams of that nickel. And we know that using our periodic table, we can convert to moles of nickel using the molar mass, which happens to be 58.69 grams of nickel. And if you do that division, it's a really small number. It's 0.00002556. And I'm carrying it out that far because I want 4 sig figs. We can do the same thing for the iodine. Iodine has a mass of 0.0067 in the problem. And we can convert that to moles using our periodic table. So 1 mole of iodine has a mass of 126.90 grams from the periodic table. Do that division and you will get 0.00005194. So again, really small number, but we don't really care that these are small numbers because we want the relationship between them. So we are going to divide by the smaller one. They both are 0.40s, and then one has a 2, one has a 5, so the 2 is smaller. 0.00002556 is our denominator in both cases. Up top, it's just the same number divided by itself, and down here, if you do that division, you'll get the whole number 2. So that's telling you that in this compound, our ratio is for every 1 nickel, there are 2 iodines. Okay, so let's make things a little bit more tricky. We're going to go back to number 1 and see if we can put all of this together. So in number 1, first off, we have 4 different elements, and second off, they're given in percents. So our first step is going to be to take the percents and turn them into masses. So we have 38.4% potassium. We're going to turn that into 38.4 grams of potassium. Again, let's assume that we're dealing with a 100-gram sample. I'm going to leave myself a little bit of room, and I'm going to jump down and go to 23.7% carbon, which turns out to be 23.7 grams of carbon. We're going to skip a little bit of room, and we are going to say that we have 1.66% hydrogen, which turns into 1.66 grams of hydrogen. And finally, let's do our 36.3% oxygen, which turns into 36.3 grams of oxygen. So now we have their masses, and that's an important step because now we can put these all into moles, and moles is the way that we can relate these things and figure out how many of each atom there is relative to each other atom. So let's do all of those really quick. We know from the periodic table our molar masses. Our molar masses allow us to tell us the number of moles in a number of grams. So for potassium, the molar mass is 39.10 grams of potassium for every 1 mole. With 4 sig figs, that gives us 0.9821. For carbon, we know that the molar mass of carbon is 12.01 grams for every 1 mole of carbon. And if you do that division, you will get 1.973, again 4 sig figs. For hydrogen, hydrogen has a molar mass of 1.01 grams for every 1 mole. Do that math and you will get 0.9821. Excuse me, that is the number for potassium. My apologies, this is actually 1.644. And then finally for oxygen, oxygen has a mass of 16.00 grams for every 1 mole. And if you do that division, you will get the number 2.269. Okay, so our next step in our poem is to divide by smallest. And we're divided by smallest so we can basically figure out the ratio of all of these. So our green number, our 0.9 number, is the smallest. We're going to divide all of these by our 0.9821. So over 0.9821, this one equals 1. If we divide this by 0.9821, this one equals 2. So far, so good. This one over 0.9821 equals 1.67. That's annoying. And this one over 0.9821 equals 2.32. And so now we have a problem. Why do we have a problem? Because even if we put these things together, right, even if we said K, C2, H 1.67, O 2.32, that's still some crazy decimals, right? We don't want that. We don't like things that look like that. We need whole numbers. And so what do? Well, the last line of your poem says multiply till whole, right? And we know from math, if we do something to one number, as long as we do it to every other number, we're safe. And so imagine that one of these decimals was 0.5. If it were 0.5, 0.5 times 2 gives you a whole number. This one's a little bit tricky, but you'll notice some fractions or decimals that look familiar. You have 0.67 and you have 0.33 essentially. So both 0.67 and 0.33 are thirds, right? You have 2/3 and 1/3. So if you multiply these by 3, you get rid of the 3 in the denominator, but if we multiply those by 3, we better multiply these by 3, and we will get 3 for the top one, 6 for this one, we'll get 5 here, and we'll get 7 here. So that is our real ratio. It is really 3 potassiums for every 6 carbons, for every 5 hydrogens, for every 7 oxygens. Now, if you're looking at that, you might ask, well, how do I know what number to multiply in this step? What number am I multiplying by? And the answer is that the decimal that you'll see will be a familiar one. It will either be 0.5, so you'd multiply by 2, 0.33 or 0.67, so you'd multiply by 3, or 0.25 or 0.75, so you would multiply by 4, right? So we'll always give you some decimals that are friendly, but in this way we can arrive at these empirical formulas, which are the most simplified version of a covalent compound, and we'll talk about how to expand this out further in our next video dealing with molecular compounds.